there is a second row coming from that one, 0 minus 8 by 3 minus 2 by 3 minus 8 by 3. Okay, now the first row is as it is. Again, just we multiply second row with minus 3 by 8. Okay, because of we want leading entry 1 here in this place, so that's why we multiply minus 3 by 8. Okay, so 0 1 0 1 1 by 4 and 1. Okay, now 1 0. So now we have leading entry 1. Okay, and we want 0 here, we want to make 0 here. Okay, this is a right, this is also row echelon form, but we want to convert into a reduced row echelon form, so that's why we multiply. That's why we multiply the second row with minus 1 by 3 and add into the first row. Finally we get first row become 1 0 1 by 4 0. Okay, and the second row is as it is, 0 1 1 by 4 1. Right, now this is a reduced row echelon form matrix. From this matrix we can solve this system of linear equations. So what is our system of linear equation from this matrix? You can see the matrix is in reduced row echelon form. It has two non-zero rows, hence the rank of A is equal to 2, correct, and the solution space is of dimension n minus r. N means the number of column. How many number of column? 1 2 3 4. So 4 number of column, right? R means rank of the matrix. Why rank of the matrix is 2? Because we have two non-zero rows in a reduced row echelon form of the given matrix. So two non-zero rows, right, and the solution basis for the dimension of the solution space, that is n minus r. N means number of column minus rank. So that's why 4 minus 2, that is equal to 2. Definitely we have to suppose, or we have to take two free variables, right? So using the matrix, using this matrix, we can write down the equation. The first equation is coming from the first row, that is x1 plus x2 by 4, that is equal to 0. Sorry, x1 plus x3, this is the third row, right? The first row is for x1, the second row is for x2, the third row is for x3, and the fourth row is for x4. Okay, so x1 plus x3 by 4, that is equal to 0. The second row, x2 plus x3 by 4 plus x4, that is equal to 0. Okay, in which column we does not have leading entry? Third and fourth column. You can see the first column we have leading entry, the second column we have leading entry, but the third and fourth column we don't have leading entry. So that's why we take x3, that is equal to k, x3 and x4, that two variables our free variables now. Okay, because of third and fourth column does not have leading entry, so x3 is equal to k and x4 is equal to t, right? Using this two, x3, the value of x3 and x4, now we can find x1 and x2. X1, that is equal to minus k by 4, x1 is equal to minus k by 4, and x2 is equal to minus k by 4 minus t. As the basis for the solution space are the coefficient of k, that is minus 1 by 4, the coefficient of k in x1, x2, x3, x4, that you have to see first of all. The coefficient of k in x1, x2, x3, x4, that is minus 1 by 4, minus 1 by 4, 1 and 0. Okay, and the coefficient of t in x1, x2, x3, x4, that is 0, minus 1, 0, 1. Okay, next question, question 2b. Why the following sets are not vector spaces under the given operations. Justify your answer. The set of all pair of real number xy with the operation x1 plus y, x1 y1 plus x2 y2, that is equal to x1 plus x2 y1 plus y2, and alpha into xy, that is equal to 2 alpha x 2 alpha y. Okay, now you can see the addition in the first example. In the first part, the addition is a standard addition, so there is no problem to solve or to prove the first 5 condition of the vector space. You can understand what is the definition of vector space, right? There are number of 10 conditions must be satisfied for a given set V, right? The first 5 conditions are for vector addition and the another 5 conditions are for scalar multiplication. In the first 5 conditions, the first one is a closeness, right? The second is commutative law. The third one is associative law, right? The fourth one is identity. The fifth one is inverse of the given matrix for addition, right? So these 5 conditions are satisfied for the given set V, then we can say that the addition is okay. Now next, the for scalar multiplication. For scalar multiplication, another 5 conditions. The first one is closeness, right? The second one is associative law, okay? The third, fourth is distributive law, right? And the fifth one and the last one is one identity, that means 1 into x, that is equal to x, right? So let's check all the conditions by one, but the first 5 condition definitely satisfied in this example because the addition is standard addition. So just we have to make sure for the another 5 conditions for scalar multiplication, maybe one of the condition definitely drop here, because the answer is already we have that this set is not a vector space, that is already we have. So we have to just find such condition, that which condition is drop here, right? So let's see. Now directly I written, here is the answer. Take alpha is equal to 1 and x is equal to 2 3, right? So what is 1 into 2 3? That is equal to 2 into 1 into 2, that is 4 6, that is not equal to x. So the last condition for the scalar multiplication is drop here. So one of the exams of vector space does not hold, so that means the given set is not a vector space under this addition and scalar multiplication. And the second one is quite easy, because the scalar multiplication is not defined here, only the addition is defined here. So you can write down that the scalar multiplication is not defined here. A scalar multiplication is not defined in R3, so the given set is not a vector space, right? So here is the complete the solution. Next question, question 2c. Let lambda be an eigenvalue of the matrix A, then prove that lambda plus k is an eigenvalue of A plus ki and k lambda is an eigenvalue of k into A. This is quite theoretical question. So let lambda denote an eigenvalue of A and lambda dash, right, denote the eigenvalue of A plus ki. Now lambda is an eigenvalue of A, that means the characteristic equation of A is determinant of A minus lambda, that is equal to 0, and the characteristic equation of A plus ki, that is A plus ki minus lambda dash I, that is equal to 0, because lambda dash is denote the eigenvalue of A plus ki, right? So using that notation. Now just simplify this equation. A plus ki minus lambda dash I can be written as A minus lambda dash minus k into I, that is equal to 0, right? So call it equation 2. This is our equation 1. From equation 1 and 2 you can see, compare equation 1 and 2, we get lambda is equal to lambda dash minus k. Lambda is equal to lambda dash minus k. So lambda dash is equal to lambda plus k. The eigenvalue of A plus ki is lambda plus k. Now second, k k lambda is an eigenvalue of ka. Okay, that we have to prove. So again, lambda denote the eigenvalue of a and lambda dash denote the eigenvalue of ka. So the characteristic equation of a is a minus lambda I, that is equal to 0, and the characteristic equation of ka, that is ka minus lambda dash I, determinant of ka minus lambda dash I, that is equal to 0. Just k will be outside, so we get a minus lambda dash upon k into I, that is equal to 0, right? So comparing this 3 and 4 equation, we get lambda is equal to lambda dash upon 4. So lambda dash is equal to k lambda. So the eigenvalue of ka is k lambda. Okay, so here is the complete the solution of this question. Next question, question 2d. Solve the following system by Gauss elimination method. 2x plus 2y plus 2z, that is equal to 0, minus 2x plus 5y plus 2z, that is equal to 1, 8x plus y plus 4z, that is equal to minus 1. And this question asked in 4 marks. The matrix equation of the given system is, now first of all we have to convert into an augmented matrix, right? So just write down in matrix equation in matrix form. The first row is coming from the first equation, 2 2 2, right, the coefficient of x y z. The second row is coming from the second equation, that is minus 2 5 2, and the third row is coming from the third equation, that is 8 1 4 to x y z, that is equal to 0 1 minus 1. Okay, so ax is equal to b. Say the augmented matrix A is 2 2 2 0 minus 2 5 2 1 8 1 4 minus 1. So here is our first process. We multiply first row with 1 and add into the second row, and we multiply the first row with minus 4 and add into the third row. Because of this is our leading entry, 2 is our leading entry. Below that leading entry we want make 0, that means we want 0 here and here. So that's why we multiply first row with 1 and add into the second row, and multiply first row with minus 4 and add into the third row. So the first row is as it is 2 2 0 2 2 2 0. Second row become 0 5 plus 2 7 2 plus 2 4 and 1 plus 0 1. We multiply first row with minus 4 and add into the third row, so that is 8 minus 8 0, 1 minus 4 into 2, that is minus 7, and 4 minus 4 into 2, that is 4 minus 8, that is minus 4. So 0 7 4 1. Second row becomes 0 7 4 1. Third row becomes 0 minus 7 minus 4 minus 1. Okay, now the first row is as it is 2 2 2 0. The second row become, now next process is we multiply second row with 1 and add into the third row. You can see this second and third row are almost same, just the difference is the sign, right? So that's why we multiply the second row with 1 and add into the third row. So the first and second row are as it is 2 2 2 0 0 7 4 1, okay, and 0 0 0 0, correct. So from this equation we get 2x plus 2y plus 2z is equal to 0, coming from the first row. The second equation is coming from the second row, 7y plus 4z, that is equal to 1. Now in first column we have leading entry, in second column we have leading entry, but the third column we don't have leading entry. So z is equal to k, take z is equal to k, hence y is equal to 1 minus 4k upon 7 is coming from this equation, 1 minus 4k upon 7. X is equal to minus 3z plus 1 upon 7. Okay, so there are infinitely many solutions. Here is a complete the solution of this question. So up to this question we solve this question paper. Thank you.